Thank you for the invitation. So today I will talk about my thesis work that was supervised by some people like Sébastien Bardin, Richard Bonichon, Mathieu Lemaire, Laurent Mounier, and Marie-Laure Potet. And so yes, my work was about verifying low-level C with inline assembly. So yes, today's challenge is what about the verification of C code, C project that contain some part of low-level code like inline assembly or external external compiled function. So we focused on inline assembly because we figured out that inline assembly is a practice well spread in software development. So for instance, we have identified that almost 10%, that more than 10% of the package written in C in the Debian distribution contains inline assembly. And another study by Rieger and al. Have shown that more than 1/4 of projects from GitHub written in C contain also inline assembly. And in fact, inline assembly is used to optimize part of the code that are performance sensitive, like for instance, multimedia library like FFmpeg or ALSA, or scientific computation like GMP. So here is an example of inline assembly, and I will come back to the structure later. So the problem with inline assembly is that the syntax of inline assembly is notoriously hard. It's well known that it is easy to make an error while writing inline assembly. And for example, the code above worked fine with a standard compiler. And then just because the compiler evolved, the version of the compiler evolved, or you change the compiler, then the inline assembly may crash, for example, with a segmentation fault. And the problem is compiler provide the syntax for inlining assembly instruction inside the C, but it doesn't understand what is the meaning of the instruction you are adding in your C code. So the compiler knowledge is only limited to the interface between the C and the assembly. And the compiler will perform some work on this knowledge. For example, it will allocate a register or make optimization on the value the assembly work on. And if there is any mismatch between the interface of the C and the assembly, they can lead to bug. So to understand the problem can arise, I will describe the structure of an inline assembly code. So an inline assembly code is an inline assembly chunk is composed by an assembly template. So it's just some strings, string of characters that contain both the inline the assembly instructions, but also some tokens like that work like printf function, for example. So these tokens will be replaced by the compiler by the actual operand that it chooses when it compile, when it put these instructions inside the code it generates. So for instance, this operand come from the interface that is composed by the output list, the input list, and the callback list. The first one describes the C operand expression or L value that will be modified by the assembly. the input list is the same C value that can be read by the assembly, and the global list is more about side effect of the assembly chunk. So, for example, it can declare that a specific register will be used as a temporary value, and so the value will be lost. Or some keyword like CC or memory indicates that the assembly chunk will have a global effect. For example, memory says that it will access memory in an arbitrary pattern. So, for example, here we can expect that it will read or write memory from the pointers that are given in argument. And this interface also contains some notation in a compact language that indicate how the compiler should instantiate the operand. So, for instance, the hem respond to a memory operand, whereas A specifies that the value result must be will be written in the EAX register, and D the EAX register, and so on. Of course, this is an example. This was an example of segmentation fault, but we also found several examples of inline assembly bugs that are that come from a mismatch between interface and the declared interface and the real behavior of the assembly. So the goal of my work was to firstly define what is the compliance of interface, of assembly interface. And of course, this must be built on a proper formalization to be able to state and verify the properties. Then we want to provide a method to check the compliance, potentially patch it when we found the compliance issue, and also, in addition, refine the interface. For instance, if we found some case where inline assembly were overstated. So, for instance, it contains constraints that are not useful for the chunk to work correctly. And of course, we want it to be widely applicable, so we want it to work whatever compiler we use, for example, GCC, CLang, or Intel C compiler, and for different architecture like x86 or ARM. The main contribution of this part of my thesis was formalization of interface compliance that take into account the difference between the compilers, and define two main properties that are framing condition and unicity condition. A method to automatically check, patch, and refine the interface based on data flow analysis and some dedicated optimization to improve the precision of our analysis. And this way we can infer an over approximation of what is the ideal interface of an assembly chunk. We have conducted some experiment of prototypes developed on Camel and based on the two platforms, Pharmacy and Binsec, developed at CA List. And so we have applied this prototype on more than 2,000 real-world assembly chunks. That come from the Debian package. the source of the Debian package. We found more than 2,000 issues, where almost all of them were deemed severe or dangerous. And we provide 2,000 patch that patch almost all the severe issues. And also we have provided some patches to the package developers that were taken, that was already taken, accepted, and taken into account on the GitHub repositories. And at the end, we conduct studies about why we found so many compliance issues and how they can affect the current state of the code. So now I will jump into the details. So first is the interface compliant properties. So as I said, we define two main properties, where the first one was split into two sub-properties. So there is framing condition and unicity condition. The first two one are easy to understand. So for instance, firm right is a property that you only write on location you were allowed. So for instance, you cannot modify something that the compiler will not be aware of. Frame read is the same for the read properties. So you will only read the values that the compiler provided to you, so have correctly initialized. The unicity is more subtle because, in fact, the unicity condition ensures that whatever the choice between the actual operand the compiler have choose, for example, if it has a choice between two registers EAX and EDX, then whatever the choice he made, the assembly chunks will have the same behavior. Of course, these properties have been formalized with the formalization of the operational semantic of assembly that we provide in the thesis. And so we are about firstly to describe them, to formally state them, and of course to verify them. So in order to check that these properties hold for an inline assembly chunk, we developed a dedicated data flow analysis. So from frame right, we basically collect all the left-hand side expressions, so all the locations that will be affected by the chunk, and we verify that all these locations have been declared with the proper right flag. For frame read, we perform a liveness analysis in order to collect all the dependencies that will be read from the C. And for unicity, it's a combination with the two previous data flow with some dedicated analysis to know if a token so an arbitrary token that can be replaced by an operand like memory or register, may impact another one because the compiler can share the same location for the two. For example, if you have an output and an input, and that the input is read before the output is written, the compiler may try to share the two values in the same registers. But for there is some situation where this value will be read after the other value will be written, and in this case, the value will be overwritten before it is actually used. That is in unspecified behavior. We also provided two precision enhancers. For instance, expression propagation, in order to reduce the set of collected left-hand side from right. So for instance, it may happen that some values are written, but then restored just before the assembly leaves the control flow. And so, for instance, it should not be considered as an issue. And for frame read, we improve the precision by tracking liveliness at bit level. So instead of word level, for instance, a variable, and so we can reduce the part of variables that are not initialized but never read, in fact. We developed a prototype we named RUSTINA that is based on the common architecture named TINA that allow to, starting from C code with inline assembly, to extract a formal definition of the template and the interface, optimize, extract the assembly, the semantic of assembly with sec, and from the intermediate representation, infer with data flow analysis the interface and can compare the inferred interface and the declared interface, and eventually to provide patch if an issue is detected. So we perform experimental evaluation of RUSTINA with several research questions in mind. For instance, how does RUSTINA perform at checking and patching the assembly chunk? But also a question about why so many issues are found but do not turn into bugs in the common in the daily life, and of course, what is the impact of the reported issues in the community, software community, and something that I will not talk about today, but what is the impact of the design choice? So, for instance, what is the gain of the precision and sensor we developed? So, like I said before, we found around 2,000 issues, where almost half of them are significant issues that can lead to a bug with current compilers. Most of them are frame right. So in fact, most of the errors are that the assembly chunk right inside the location without the compiler is aware. And the other are about locations that are read without being declared, and some unicity issues. In average, in new benchmark setup, it takes 2 minutes to analyze all the 3,000 assembly chunk, with an average time of 40 milliseconds per chunk. And at the chunk level, we can see that almost all of the chunk are patched. So before, only half of the chunks were compliant, whereas at the end, with OPatch, 97% of the chunk are compliant. And at the package level, we can see that we are able to patch almost half of the package that were not compliant, that contain chunks that are not compliant. Yet, if we take a break, we can see that we found 2,000 issues, compliance issues, but of course the project doesn't crash, doesn't produce segmentation fault all the days. So why is that? Why the issues do not turn into bugs more often? And to answer this question, we tried to stress out the compilation process, and for instance, to increase the optimization levels of compilers. So for instance, using O3, or to use LTO optimization, so link time optimization, that allows the compiler to perform more optimization with a better knowledge of the whole application. And with these studies, we found that almost all the issues come from 6 recurrent patterns, and 90% of the issue, 90% of the issue comes from 3 recurrent patterns, and on these 6 patterns, 5 of them can lead to bugs during our experiments. So, for instance, these patterns are the fact to omit the flags registers inside the clubbers, the fact to use ebase without defining into the clubbers, the same with ESP registers. Then the 3 last patterns are about the memory. So, for instance, when you forget to declare that you assembly chunks may access or write memory, and different kind of register, ASCMD register. So, for instance, MMX or XMM register that are a single instruction for multiple data. And what we can see is that in our experiment, we with different aggressive techniques like inlining. So in fact, using high-level optimization of compilers, or cloning. So for instance, if we just take an assembly chunk we found in some project and say, oh, it worked for this one, so I could just copy it in my projects and it will work. We were able to break and to produce a compilation bug with this pattern. And of course, there is also the bugs that we already found in the GitHub histories of the different package we analyzed. Then this study also permitted to submit several patches to project. In fact, we sent it almost 100 patches to head project, and 7 of them have already applied them. So all of this project except FFmpeg that is already that is still analyzing the patches. So in conclusion, we have given a formal definition of the interface compliance. With dedicated data flow analysis that allow check, patch, and sometimes refine the assembly chunks interface. And this impacted the software community by providing patches that improve the robustness of the projects. This was for the first part of my thesis. I will also talk briefly about the second part, that is verification oriented lifting. So the objective, the goal of this part was to allow the verification of the C code at C level. So, for instance, using C verification techniques like, for instance, CLI or pharmacy tools. And for this, our proposition was to lift, so translate the semantics of inline assembly into an equivalent C code that could be analyzed with a tool that work at C syntax. The main contribution were the development of dedicated high-level structure recovery mechanism. Like, for instance, we identified threads that can lead a bare translation to lead to bad verification. So, for instance, if we simply translate the semantic of the assembly into a C, it can appear several low-level details that the C tools are not used to work with. And so we provide optimization of the intermediate representation that allow to produce a more high-level C code that is more easily analyzed. We provide a validation path to ensure that our optimizations didn't change the semantic of the produced C code in regards to the assembly semantics. And we perform different analyses to different experiments about the capacity of TINA to lift assembly chunks and the impact of the optimizations we provide on the verification tools. So this part is implemented on top of the common architectures. And just a word about the results. On the 3,000 assembly chunks we found in the Debian distribution, we were able to extract the semantic of 2,500 blocks, and to lift all the chunks, to lift in C all the chunks, we were able to extract the semantics. And of course, to validate all the translation with all dedicated techniques, with an average time of 600 milliseconds per chunk. And of course, we conduct some experiment on ARM architecture to confirm the genericity of our approach. And we also show that our optimization, based on some criterions, improves the verification of the code compared to the absence of the translation that will be really basics. So, for instance, with symbolic execution, the simplification allows to explore more paths because the constraints will be more easier to solve. With pharmacy, we reduce the number of alarms, and so we were able to prove that more code are are safe without the addition of any new annotations to guide the analysis. And for example, for some deductive verifications, our optimization allow to perform to discharge fully the proof, whereas without it is not possible to prove anything. So, in conclusion, at the level of my thesis, we proposed three main contributions that are the definition of a semantic operational for inline assembly based on the documentation and to replace the missing formalization of the semantic of inline assembly. A method to check, patch, and refine the interface. So based on the formalization of interface compliance that allow us to perform a real study and to provide patches to software developers. And a method to help verification of C projects that contain inline assembly. Yes. And so based on the optimizations and tailored post validations that help to ensure to ensure trust of the translations. So thank you for your attention, and if you have any question, you are welcome.